Today's topic is on diode circuit for the DC analysis and models of diode circuit. The objective of the lecture is to examine DC analysis techniques of diode circuits using various models as we are going to be considering. So the various models are the ideal diode, the piecewise linear model, the graphical analysis, trial by error, and the piece-piece model. So we are going to be considering all these models to describe diode characteristics. So we have seen that the diode is a two-terminal device with non-linear IV characteristics as opposed to a resistor, which is also a two-terminal device, but it has a linear IV characteristic curve. And the analysis of nonlinear electronic circuits is not as straightforward compared to the linear circuits. However, nonlinear electronic circuits are very important in semiconductor electronics, and they can be used for various purposes. And one is the conversion of AC voltage to DC voltage, and also the implementation of logic function. So models or mathematical relationship that describe the IV characteristics of some electronic circuit elements, they allow us to analyze and design circuits without having to fabricate and test them in the laboratory. So once we have the model, maybe it's a spice model, or it's a mathematical model, or it's a piecewise linear model, then it is possible to be able to analyze and design the circuit without being without fabricating it, like physical fabrication and testing. So before we start, we'll look at large signal models. So large signal models, they describe the behavior of the device when there's relatively large changes in current and voltages. So, and we also have small signal models that describe the behavior of the diode when small changes in voltages and current is applied. So in order to begin to understand the diode circuit, we are going to consider a simple diode application, and we would start with the ID diode. So the ID diode is a diode that has this IV characteristic. So when reverse bias voltage is applied, there is no current flowing, so it's essentially an open circuit. But when it is forward biased, so when the current through the diode is greater than 0, the voltage drop across the diode is 0. So when it is a short circuit, the voltage drop across the diode is 0. So this is the ideal diode. So when the reverse bias voltage is applied, the current through the diode is 0. But when the diode current is greater than 0, the voltage drop across the diode is 0. So this is the ideal diode. So we'll use the ideal diode to describe a rectifier circuit. So the rectifier circuit is shown in this figure. So this is the rectifier circuit. So you have a sinusoidal voltage. So the sinusoidal voltage is also called a sinusoidal input. So it repeats every cycle. Then you have the diode, and you have the resistor that is connected in this way. Then the voltage, the output voltage is measured across the resistor. So during the positive half cycle of the input, because this is a sinusoidal input, is an AC input. So during the positive cycle, so when this voltage is positive, so remember that we are considering the case of the ideal diode. So in the case of when there's a positive sinusoidal input for the positive cycle, a forward bias current exists in the diode and the voltage across the diode is zero. So given that the voltage across the diode is zero, the input voltage is equal to the output voltage. So the input voltage is equal to the output voltage. But during the negative cycle, the diode is essentially in reverse bias uh, condition. So it is in the reverse bias condition. So essentially it's an open circuit, and therefore the diode current is equal to zero. So therefore the output voltage is equal to zero. That's for the negative half cycle. So it repeats again. So for the positive half cycle, the input is equal to the output. So over the entire cycle, the input signal is sinusoidal and has a zero average value. So because you have positive and negative, so averagely is zero. But when it's the output signal, when it passes through this circuit, it only has positive values. So as a result of that, this circuit is set to rectify the input signal. So it's called a rectifier circuit, and is a first step in converting an AC signal or an AC voltage to a DC voltage. So as we mentioned previously, when we are analyzing, the topic is to analyze diode circuits. So it's not as straightforward as linear circuits. So we are going to be looking at 4 approaches that we can use to do the analysis. One is iteration, the second is graphical techniques, and the piecewise linear modeling and piecewise computer analysis. So we start with the first one. So we're going to do the iteration and the graphical analysis together as they go hand in hand. So the iteration method is simply a trial and error method to solve a problem. So we are going to consider this circuit, and we are going to uh, find the diode current and the diode voltage through iteration and through graphical analysis. So the first step is to do is to the first step is considering this circuit, then applying KVL, that's Kirchhoff voltage law, because Kirchhoff voltage law applies to both linear and non-linear elements. So writing the Kirchhoff voltage law, so VPS is the power supply voltage, ID is the diode current, VD is the diode voltage, the drop across the diode. So writing the KVL, so around this slope, so you have VPS is equal to IDR plus VD. So this is the KVL of this circuit. Then you can simply make ID the subject of formula, and we arrive at this equation. So we already know the IV characteristics of a diode. The ideal IV characteristics of a diode is given by this equation, which we talked about in the last class. So the I and the V, the IV characteristics of a diode is given by this equation. So when we substitute this equation for ID and we put it inside this equation, we arrive at this equation 1.23, and this equation 1.23, it contains only one unknown, which is VD. So the VPS, which is the power supply voltage, is known, the reverse bias saturation current is known, the value of the resistor is known, VT is known, N is known. So you might say that you can just solve for the value of VD, but unfortunately it's not possible to solve for the exact value of VD because this is a transcendental equation. So uh, one is not really able to solve for VD directly. So hence the use of iteration, trial by error, and graphical approach. So in this example, we want to determine the IV, the ID, the VD, and the ID for the circuit in figure 1.28. So we want to determine the voltage drop across the diode and also the diode current. So we've already arrived at this equation and we want to get VD. So we'll just substitute the values because the values are already specified here. So we'll substitute the values inside. Then we'll begin to use the trial and error approach to get the value of VD, because like I said earlier, it's not really possible to develop an equation that would give you the value of VD. So we begin to substitute different values of VD and see if we arrive at this 5, which is the power supply voltage. So to make it easier, I have an Excel sheet here. So this is the value of the VD. So like I said, I'll begin to substitute different values of VD. Then I will see which one gives the value of 5. So I have this Excel sheet here. So I have different values of VD, 0.6 to 0.7. Then this is the power supply voltage. So I used Excel equation to write down this same equation here in Excel format, and it calculated the value of VPS for me. So when VD is 0.6, you have 2.7 volts, but remember that it's 5 volts we want. And when we move to 0.61, we got 3.7 volts. So I began to change it till we get to 0.7 volts. So 0.7 volts is not practical because VPS is like 99 volts. So the closest value of VD is 0.62 volts, so which will give you 5.16 power supply voltage. So it simply means that the VD is between 0.61 and 0.62. So that's why here subsequently I decided to vary it from 0. Because I've already known that the value of VD is going to be from 0.61 to 0.62. So I begin to do small changes from 0.61 to 0.62. So when I do this small change, I calculate my value of power supply voltage, and the one that is closest to 5 volts is 0.619 volts. So remember that if VD is 0.2 volts, it's 5.1 volts, and if it's 0.619, it's 4.99 volts. So we just say that our VD is equal to 0.619 volts, because then we get approximately 5 volts on the left hand side of the equation. So remember we are doing the trial and error approach. So through trial and error we've gotten the VD. So in order to get the value of the current, you can just simply substitute VD either into this equation or into this equation, but this equation is much more simpler but both of them will arrive at the same answer. So when we do just that, we arrive at 2.19 milliamp. So we've been able to calculate the diode current and the diode voltage through the trial and error method. So we are going to consider the graphical approach to get this to get the current, the diode current and the diode voltage. So from Kirchhoff voltage law, we arrived at this equation. Then we make ID the subject of formula like we did, and this is a linear equation and it's called the circuit load line, and we want to represent it in form of a linear equation, which is y is equal to mx plus c. And remember, when we're talking about the IV characteristic curve, the I is always on the y-axis, while the V is always on the x-axis. So putting the I on the y-axis and this VD is on the x-axis. So putting this linear equation, putting it in this form. So we are interchanging it. So minus 1 over R is the M, which is the slope. Our X is the VD, so which is the diode voltage. Then the C, the intercept, is VPS divided by R. So I'm just putting this equation in form of y is equal to mx plus c. So we arrive at this equation. So like I said, this equation is the load line, and also the IV characteristic curve of the IV characteristic equation of the diode is given by this equation here. So what we are going to do is that this equation here and this equation here, we are going to graphically plot it. This equation is called the load line. So going back to Excel, so Excel, I have VD. So I'm sweeping the VD from 0 to 5 volts. So the VD is from 0 to 5 volts, which are manually typed. Then the ID is simply given by the load line. So this equation for the load line here, so 1 minus 1 divided by R times VD plus VPS over R. So this equation is the equation here, but in Excel form. So I multiplied it by 1000 because I want the result to be in milliamperes. So using this formula for the load line, I got the different values of ID. Then for the second equation here, which is this equation here, so I just put this equation in an Excel format to arrive at this equation, so which is in the Excel format. So this is the saturation reversed by saturation current exponential VD divided by VT minus 1. So using these different values, so sweeping the values of VD from 0 to 5 volts, then arrive at this. Then I plotted IV versus VD for this curve. So this curve here is the ID versus VD, and this curve here is the ID versus VD for both equations. Then the point of intersection of the load line with the IV equation of a diode, the point of intersection will give you the diode voltage and the diode current. So this is using the graphical approach. So the point of intersection, like we see here, the point of intersection is the ID is about 2.2 milliamp and VD is about 0.62 volts. So that's the point of intersection. So here is 2.2 milliamp and here is 0.62 volts. So that will give you the diode current and the diode voltage. And the point of intersection is called the quiescent point or the Q point. So we are simply plotting the IV characteristic curve and the load line, and the point of intersection would give you the values we are looking for. So the graphical method, but it yields accurate results, but it's not really very straightforward. But it's useful in the sense that it's the approach, you can use it to visualize the response of a circuit, and the load line, the concept of the load line is really used extensively in the evaluation of electronic circuits, so it's worth noting. The third method you're going to use to analyze a diode circuit is the piecewise linear model. So the piecewise linear model is a simpler way to analyze the diode circuit and to get the approximate diode current and diode voltage. So for the piecewise linear model, we define two scenarios. So the first case is when VD is greater than V gamma. So this is our V gamma. So the V gamma is going to be defined, is going to be stated. So when VD is greater than V gamma, we assume a straight line approximation whose slope is equal to 1 over RF, where the V gamma is called the turn-on voltage or the cut-in voltage, and RF is called the forward diode resistance. So when VD is greater than V gamma, so essentially in this point, you are assuming a straight line approximation of the IV characteristic curve of a diode, and the equivalent circuit for this linear approximation is a constant voltage source in series with a resistor. So the equivalent circuit of the part when VD is greater than V gamma is a constant voltage source V gamma in series with the forward diode resistance RF. Remember, we are assuming two scenarios. So for the second scenario where VD is less than V gamma, so in this case where VD is less than V gamma, so we are assuming a straight line approximation parallel with VD axis at zero current. So essentially in this second condition, it's an open circuit, so the diode current is equal to 0. So this method models the diode with segment of straight lines. So that's the name piecewise model. So it just models it as a straight line. So the parts where VD is greater than V gamma and the parts where VD is less than V gamma. So if RF is equal to 0, so this is the IV characteristics they can see. So this is the piecewise linear model of the diode. It's a constant voltage source in series with a forward diode resistance. So we are going to use an example now to determine the diode voltage and the diode current in that same circuit. So using piecewise linear approximation, so the V gamma is given as 0.6 volts and the forward diode resistance is given as 10 volts. So the ID is just given by this equation. So this equation is also the same equation we have here when we did the KVL. When we did the KVL analysis of the diode. So it's just this equation, but in place of VD we have V gamma, and in place of R we have R plus RF. So we just simply use the piecewise linear model to and put in the values we already have. Then we get 2.19 milliamp, which is about the same diode current we have gotten previously. Then to get the diode voltage, so we're just simply going to use the KVL around the model of the piecewise equivalent model, piecewise linear equivalent model of the diode. Then using this equation, which is the KVL around the loop, then plugging the values of ID you have, we get 0.22 volts. And we are also asked to calculate the power. So the power is equal to IV, so which is the diode current multiplied by the diode voltage, which is 1.36 milliamp. So this is the piecewise linear model, and as you can see, it's a very straightforward model compared to the trial by error and the graphical method, because we don't really need to plot. So the diode current, this diode current is independent of RF, because this RF, if it's kind of very small compared to the R, so you can kind of omit it if it's really very small. Then we also say that the cut-in voltage, it's if we change the cut-in voltage, because in this example the cut-in voltage was 0.6 volts, so if we had changed it to 0.7 volts, we would have arrived at a current of 2.15 milliamp. So what this means is that the current is not really a strong function of the cut-in voltage. So it's not really a strong function of the value of this V gamma. So we normally assume a cut-in voltage of 0.7 volts for silicon PN junction diode. So we can use the concept we already know of the load line to do a further analysis using the piecewise linear model. So from the Kirchhoff voltage law, so you have this V gamma, so V gamma in place of VD, so where V gamma is the cut-in voltage or the turn-on voltage. So you can have different load lines for different values of power supply and different values of resistor. So when we plot the different load line, so we are going to, this is the first load line, and these are the different load line, and we say that the intersection of the IV characteristic curve with the load line is called the Q point. So for different values of the power supply and resistor, we have arrived at different Q points using the piecewise linear model. So for the piecewise linear model, you just have like two scenarios. So where VD is greater than V gamma and where VD is less than V gamma. So this line is given by a slope of 1 divided by RF. But that RF can be neglected if it's really very small. So conversely, you can also apply the concept of the load line to and the piecewise linear model when the circuit is in reverse bias. So here you are applying a positive voltage to the negative side of the diode, so indicating that it is in reverse bias. So when you do the KVL around this loop, so it's VPS is equal to IPS multiplied by R minus VD, but IPS is equal to minus ID, so it becomes this equation minus VD. So from there we can make ID the subject of formula. So this is essentially the load line. So the load line can be plotted, and you have the ideal IV characteristic. So the point in which the IV characteristic curve and the load line meets is called the Q point. So in the case of the reverse bias case, you have the minus 5 volts, so which is the point of the which is the Q point. So the final method we are going to consider to analyze a diode circuit is the SPICE. So using a computer program called SPICE. So SPICE stands for Simulation Program with Integrated Circuit Emphasis. So we are going to draw the circuit on a PSpice program. So here is the circuit. So here is the circuit on a PSpice program. So you have the VPS represented by V1, which is at 5 volts. You have the resistor, which is 2 kilo ohm. Then we have the diode. Then this point here is the probe for the current, and this is a probe for the voltage. So for the simulation profile, we are going to sweep the power supply volt. The power supply voltage is going to be swept from 0 to 5 volts in steps of 0.1 volts. So is this V1 that is going to be swept. So when we want to get the curve, so I click on run SPICE. So the SPICE program. So when I click on the run SPICE, it's going to produce the curve here. Just kind of slow. Yeah. So this is the curve here. So this is the IV curve. So here is the power supply voltage being swept from 0 to 5 volts in steps of 0.1 volts. Then here is the current. Is the current here. So this is the D1, the current, the diode current, and here is the voltage, not the diode voltage, but the power supply voltage being switched from 0 to 5 volts. So as you can see, from 0 volts to about 400 millivolts, that's 0.4 volts. It's kind of linear. Then we can see that the maximum value of the current is about 0.65. The maximum value of the voltage is about, because here is 0.8 volts, here is 0.7 volts, so it's about 0.68 volts. So this axis is a diode voltage, and this axis is the power supply voltage being switched from 0 to 5 volts. So sorry, initially I said that this axis is the current, but it's actually the diode voltage. So is this voltage diode, so the voltage across the diode. So like I said earlier, so the maximum value of the diode voltage is about 0.68 volts. So we said that we just set the cutting voltage or the turn-on voltage of the diode, we set it to 0.7 volts. So we now want to plot the current, the diode current, as a function of the power supply voltage. So to do that, let's click and add plot. Then on the new plot, right click and add trace. So is the current as a function of the voltage. So this is the diode current as a function of the voltage. So here we can see that the maximum current across the diode should be about the maximum current is here. So it's about 2.2 milliamp, and we can see that the the value of the current, it's essentially zero, but when it gets to about 0.6, 0.7, when it gets to about 0.7 volts, then it begins to increase like linearly until it reaches the maximum value of about 2.2 milliamp. So these are the different methods that we can use to analyze the the models, DC models of a diode. So which we have considered in this particular lecture.